systems do is, in the sense, there are multiple ways we are trying to figure out how we can make the underlying model. And this was the case where we said neural network, right? And what we spent time yesterday and a couple of minutes today is that what's the scientific background that is basically giving value to neural networks. This was, I think we didn't cover this slide yesterday, right? We did. Okay. All right. So this is a little bit of a schematic on top of the brain where if you can imagine that these are the specific neurons and these are the connections between these neurons. Clearly, that's very simplistic model. As I said, that there are like billions of neurons, and then among the billions of neurons, if you want to kind of map them as a graph, there will be tens of billions of edges. So this is a very simplistic implementation. We're going to make it even more simpler for today's purposes, right? We're going to study, or we're going to study one neuron at a time. We're going to see what the one neuron, because if we know how the one neuron functions, then we can make it, okay, how will two neurons functions, and how will 2, 3, 4, and n number of neurons functions, right? So we're going to start with how does one neuron functions, and can we model that in our code? Because at the end of the day, we're not creating mechanical brain, we are creating an electronic brain, right? So how can we take what we know about a neuron and implement it in our code? That's what we are trying to do here. So we'll start with one single neuron, then we will start with connecting two neurons, and then we'll see how it leads to what's known as neural network. Because once you create a network of neurons, that's a neural network. And these neurons are not the natural or the live neurons, these are artificial neuron. So the approach is called ANN, artificial neural network. That's where it comes from, right? So massively parallel distributed system, because that's what we are going to end up with. Each node is a neuron. They are connected with each other. And if you think about it, majority of the research in last, I would say 15, 16 years is to find out the architecture of this network. So it was understood how neuron functions, it's understood how they connect with each other. Now we have to figure out what's the best way to connect them. That's what is the neural network architecture is. And if you see that there are hundreds of papers, research published, which create these networks or different architecture of these networks, what is it driven by? What the goal is, what the end result is, and then you discover what's the best architecture for these neurons will be. So clearly parallel distributed, but then how exactly it is designed, it depends on what exactly is the task we are trying to achieve. So we'll come to that as we go along. Whatever is the knowledge. Now what is the knowledge here? The knowledge is how the network is connected, that's number one. And then every edge of the network carries some weight. Now that's the part of the learning exercise. Now we will go into more detail that today. That is all what we are saying, that is the computer representation of knowledge as we think today how our body processes it. Is that part clear? Right? Okay. So that brings me to two other things in terms of the mathematics that I have talked about. Remember, we said 4 things. Anyone remembers what were those 4 things? Calculus, linear algebra, probability, matrix multiplication is linear algebra. Okay, all right, think about it. What we are going to do is that we're going to touch a little bit of calculus today. Now, how many of you remember high school intermediate calculus? Any idea? What's differentiation? Actually, I should start even before that. What's a function? There's a saying, actually, I don't know who actually has said this. All science, all mathematics is all about knowing functions. So what is a function? Anyone can tell me? Can you give me an example of a function?
Every element in the domain must connect with the codomain, and every element which is domain must map to only one element, single element in the codomain.
Yes. So from definition perspective, it's good. And this is something that actually, okay. So I've also studied here, and that's the difference I'm going to tell you is that just don't stop at the definition. See how you are using it. From definition perspective, you're right. Okay? A function basically starts with two sets. You can call it domain and codomain. The days when I studied, I think it was called domain and range. If anyone has used the word range? Yeah? So a function basically is a mapping from one element of a domain to a one element of a range, right? That's what is a function. So a typical function f of x will take any value of the x from the domain and map it to some value on y, right? But what does it do for us? What is a function? There has to be a reasoning if we are studying it, right? What is that reason? Okay, so, and I'm digressing a little bit because we're going to talk about functions a lot today, okay? So I just want to make sure that you understand functions first. So, every natural phenomena in the world can be represented using a function. Now that's what this first line goes, the functions rule the world. Any natural phenomena that you observe in the world, if you want to describe it mathematically, the only way to do it is have a function. Okay? Let me ask another question. Have you heard a term called curve fitting? We did this yesterday, if you think about it. I was talking about queuing theory, right? What was the queuing theory? It was modeling a certain behavior, right? That behavior could be that you going to a post office. Post office has 3 clerks or 3 counters, but there are 30 people. If you want to study that phenomena, right? I told you that there's a study called queuing theory that you can use. Very first thing in the queuing theory is that you want to model the event. The event is the arrival of a customer. How you model that event, I didn't go this much detail yesterday, is that you try to find a mathematical function that mimics the arrival of a customer as an event. What does it mean? If you want to sample an event, what you're going to do mathematically, you're going to say that, give me a function from this, give me a sample from this function. That's what the function is working. So what are we doing here? What am I saying? Any natural phenomena can be represented by a function. Why do you need a function? Because if you want to study the natural phenomena scientifically, when I say scientifically means you're trying to create a model and then argue about that phenomena. So far with me? Feel free to ask questions because otherwise you will lose it an hour from now when we are talking about, say, the neurons. Okay? So, any natural phenomena can be represented using a function. Why do we need a function? Because we want to study that phenomena scientifically, either by using some kind of maths, equations, computers, whatever that may be. Right? So, anything that you want to study about, and it doesn't matter. I mean, I gave you the example of the post office. If somebody is studying stock market movement, all you're trying to figure out is that which function best approximates for my use case the movement of the stock price. It doesn't matter what phenomena you take, you need to model it as a function if you want to study about it. Curve fitting. Now, how do you know which function best approximate the natural phenomena?
Nonlinear function, any nonlinear function.
How do you know which nonlinear function or nonlinear function? And why not linear function?
Because in nature,
let me ask you a question here. When you are 1 year old, you have a certain height. When you are 20-year-old, you have a certain height. Is that height progressing with the age linearly or not? So, I mean, we can't say that they're all non-linear. I agree with the general thrust of your point, but I'll say again the same thing. When you're making a statement which is so definitive, that's the end of the science, because you've already declared that every natural phenomena is non-linear. If I have to say, I'll say that most natural phenomena are non-linear. I don't know about all. I'm too small to know about all, right? So just let's make it that clear. Okay, the point I'm trying to say is that what is curve fitting? Because you don't know which function best approximate. No one knows it, right? Maybe someone, Almighty God, knows it, but then I don't know it. Many people, or almost no one I know, knows that by just looking at a phenomena, they can tell you which function is approximating it. So you start with saying that you start with observations, and then say that given these observations, can I find a function that fit these observations? So let me take the same examples. You plot age and weight, age and height. I mean, it can be age and weight also. And then you say that 1 year, 2 year, blah, 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 up to let's say 19 years. Assuming that at 19 year, the height plateaus out. I mean, it could be 19 for some. And then you have these data points basically. I mean, this may not be exact line, but some kind of this observed behavior, you will see that as the age goes up, height also increases, right? And I'm going a little bit more in terms of the mathematics here. So you'll say that this sequence of observation is monotonically increasing, right? Now you're saying that if I want to approximate this natural phenomena as a function, I need to approximate a function. Yeah? Somebody might say that, okay, this is a line which is very well approximating that function. You agree? Somebody might not be happy with it, says, no, I think this is the line that's approximating the function. Theoretically speaking, there's infinite number of functions that you can apply. If you're using this kind of function, does anyone know what is it called?
Y is equal to mx line.
Yeah, it's a linear function basically, which means that there's only one dependent variable for each independent variable, right? If you take this kind of a function, what is that called? I mean, it's nonlinear, obviously. It's polynomial. A polynomial will have a degree of degree 2, 3, 4, 5. I'm sure most of you should know about polynomials, right? Okay. Now, all of this was a background to come to the differentiation. Okay. Let's start the calculus now. What is differentiation of a function? Because that's what you do, right? When you're learning the differentiation, you were learning differentiation of functions, right? So what does the differentiation do? Okay, let's just go here a little bit. What do we used to say? D over dx? Yeah? Y, where y is a function. If y equal to, let's say, 2x, is that a linear or a non-linear function? Linear, right? Something like this. Maybe not exactly this. Can someone tell me from their old high school days or intermediate days, what's dy over dx if y is equal to 2x? Who said 2? Yeah, 2 is right. What does this signify? What does it mean? Which was my original question. What is the differentiation?
It might be the y increases twice the rate of the x.
Right. For every delta change in x, the y changes twice that amount. So differentiation is calculating rate of change. Right? That's what differentiation is mean. That's all it is what the differentiation does. Now can someone tell me why are we interested in that? Our end goal is same. We're trying to build an intelligent system, right? I've said this so many times, right? Now, starting day before yesterday, we have reached a point where I'm saying that I'm interested in finding out differentiation of a function. I just explained why function is important, because every natural phenomena can be approximated as a function. Now I'm saying that I need to know the differentiation of function. Think about what we talked yesterday and day before. Why are we interested in a differentiable function or differentiation of a function?
We want the desired output and the actual output to be same, or usually tends to be.
Yes, because our end goal is to make sure that our network, neural network, learns to give us the right answer. And what did we say yesterday? If the observed output is not same as desired output, we need to go back and make the change. And then what else did we say? The change should be equal and opposite in direction. Now, if I am saying today that every phenomena can be observed as a function, then to apply the corrective measure, which is in the opposite direction but same as the change that we look for, we need to first calculate the change between the desired and the observed. Right? And how do we calculate the change? You use differentiation. So if you can model your desired output as a function, then the difference or the rate of change between the function that you desire and the function that you are achieving gives you an idea how much do you need to change, or how much the learning in your network needs to change so that you come together. Does that make sense? All right. Let me do one more thing before we get back onto our schedule here. And this is also you must have done, if not in your 12th grade, maybe in your undergrad, whenever you did. The curve fitting, how do you know which curve is better? Is the blue line here better, or the blue line or the red line here is better? Anyone remember something called MSE? What is mean square error?
Square of the errors.
Right. And what do you do with it?
We try to find out the so that we can find the perfect line.
Right. So I'll again say that let's use the word correctly. We're not finding the line, we're finding a function. We're not finding the perfect, we're finding the best fit, because that's what we are doing. So if we have multiple candidate functions or potential functions, let's say f1 and f2, how do you find out which one is a better approximation of whatever the phenomena we are looking at, right? So what you're doing is that if, let's say, our original point was here and this function is predicting it here, this is the error. Now some errors are in one direction, the other errors are in the other direction, right? Let's say this point is here. So if you're going to simply sum them up, they are basically going to cancel out each other. So you square them. And why you square them? Because the negative numbers become positive when you square them. Now what you do is that you say that you calculate the error this way for all your known points for function 1 and function 2, and then you say that I will take the function more approximate or better approximating this phenomena if it has the least amount of mean square error, right? Make sense? Okay, so let's relate it what we were doing earlier, and we will talk about these terms there again. So we will define something called a loss function. A loss function basically tells you how much is the difference between what you are observing versus what you desire. Our goal will be to obviously minimize the loss function because we want to find the best approximation, right? And then we need to find a way so that you could minimize the loss function. So now if we want to define theoretically, what are we doing here? We are trying to develop an intelligent system, AI system, which will have some goal. That goal will be somehow represented by a function. That function will be approximated by what we call neural networks. That neural network will give us some output. If that output is not same as desired output, we will calculate a loss function, and then we will continue to change our network so that the loss function gives us minimum error, so minimize the loss function. Right? Simple? And how we will try to do the minimize the loss function? At every point when we are getting the observation out, we are going to calculate the rate of change. The rate of change which will take us closer to our minimizing the loss function. Clear? Okay. In general, all optimization problems will be of the same type. You have a loss function, you want to minimize the loss function, and you're trying to figure out whatever the connections are. Okay. All right. Now, one more thing which was here is the learning process. We talked about it yesterday. The learning process is basically taking the knowledge you have represented and applying it to an unknown situation. And how do you know if the learning is happening correctly? If you are minimizing your loss function progressively in each round of learning, you're learning, right? Same thing if you think about it. If your goal is to score 100 out of 100, on the day one you scored 30 out of 100. Every progressive learning, if it's taking you minimizing your loss function, which you started with 100 minus 30 as 70, your learning is happening. Right? So it's the same thing. All right. Any questions here before we continue?
Sir, why do we calculate loss function? Because when we draw two different lines, and find which line is better, so then, sir, why loss function?
Okay. The loss function has nothing to do with the lines, basically. So let's say you're learning, you want to learn AI, right? And as I said that your goal is to score 100. On the day when you tested and you scored 30. Now what do you want to do? Your loss function or your difference between the two is your negative 70. Now you want to do in your learning whatever reduces this number. So you're minimizing this number, trying to get it as close to 100. Right? So that's your loss function. Now, let's say I'm offering one course, so that's your one choice, course 1. Let's say someone else is offering another course, course 2. It's in your interest to find out how can you quickly minimize this loss function. So you would see that, am I learning, is my learning happening so that I'm minimizing this function? Maybe not taking it to 100. Next day, let's say it becomes 35. You're making a progress in the right direction. Then it becomes 55. Then it becomes 75. So what you're doing is that you're minimizing this loss. The loss is where you want to be and where you are. If you are narrowing it down, you're going in the right direction. Now, how much effort do you need? You'll say that, okay, I only made a progress of 5, whatever the unit is. Reverse of that. So, lower the gain, higher the effort you need to grow your learning. Right? Remember the example I gave you yesterday when you were learning to ride a bike. If you are falling on the left side, you overcorrect to the right side. Now you're falling to the right side, so you correct and find the right balance. Same way. If you have a very small growth, you need a lot of effort. If you are growing fast enough, then you can possibly reallocate your time or whatever the case may be.
But how we can know that we want to minimize loss here? Because when we predict some models, but how can know my prediction is close to my desired output?
You need to know what your desired output is. That's your supervised learning. You know the answer. See, okay, so it's a good question, but it's the same thing. We said the learning happens in 3 different ways. the supervised learning, unsupervised learning, and reinforced learning. We're talking about the supervised learning where you know that given this input, this should be output. Now we are trying to figure out how close you are. Right? When you're trying to ride or learn to ride a bike, you know what your goal is, which is not to fall down on one side. So you know what your goal is. You need to keep correcting yourself so that you don't fall down. So in any learning, you are trying to minimize the loss function. That's what you're doing. Right? Okay. So let's move on here. I think I may have already said all of these things. It's always a function approximation. That's what the artificial neural network does. What you're trying to do is to learn how the brain is functioning, and you're trying to mimic that. Knowledge is acquired by environment through a learning process. That's what we are doing this, supervised learning. We'll give it examples. We know the right answer, and we'll see if the model is predicting the right answer or not. The connection strength among neurons are used to store the acquired knowledge. Now, I have not touched upon this yet, but we will talk about that next. Right? Now, these networks may be called shallow or deep. We have, I mentioned deep. Does anyone remember how we defined the deep neural network yesterday? Yes, different layers. If you have multiple levels or layers, it will become deep network. But we will start, as I mentioned earlier, with one single neuron and then two neurons, and then we will keep on adding layers to it. So we'll start what is known as a shallow neural network. All right, everyone's clear so far? All right, let's try to say, how does a single neuron look like? So I'm going to do it in two different ways. We'll first look at a little bit of mathematics. So go with the assumption that what I'm saying to you is meaningful, and then we will go back and look at the neuron. Neuron, as neuroscientists have told us that it functions. Okay? So let's look at this one. And make sure that you understand this, because if you understood this math, unfortunately today is probably the most math heavy day that we are going to have in these 10 days. So wherever you are not very clear, just raise your hand and ask me the question, or ask me to explain to you if you want to. Okay? If some of you who have not done, let's say, up to partial differentiation, obviously I can't teach you in half hour all the way starting from function to partial differentiation. That's okay. I mean, today is the most math heavy day. Let's just put it this way. So don't lose heart if you don't follow 100%, but let's try to follow as much as you can. Okay? All right, so this is a neuron. Okay, what did we say the neuroscientists have told us is that it can take multiple inputs because it can be connected with multiple different neurons. What we are doing here, we are defining a mathematical model which we think approximates how a single neuron functions in our brain. That's what we are doing. It's a model. We don't know whether this is right or wrong, correct or incorrect, partially correct or totally incorrect. We don't know, because every model when you start constructing, you don't know whether it's doing it right. You're always going to test it and see. How do you test it? Is it giving the same desired output when you actually run it through? Okay, so our model basically says that it can have n number of inputs. N can vary from 2 to whatever that. Generally, our assumption is that a neuron with single input may not convey a lot. Now, based on today's learning, right, things may change. The neuroscientists can find something else. Computer scientists can find maybe use of one single input into a neuron, but we are not there yet. So let's say 2 or more inputs into it. What does a neuron do? We were told that it is summing up the inputs. What the computer scientists, after experimentation, researchers have figured out that the best way to approximate how a single neuron functions to what is happening in our brain is not just simply summing up the input current that is coming in, but actually applying some weights. What does it mean is that not every input has the same influence on the eventual output. Okay. Now, if you ask me why is that the case, it's just like any other physics laws. Like you have laws of Newton's laws of motions. Newton observed certain thing and then he codified them in a law. Those laws have hold up until now. I mean, they are working. So the same way, what the researchers in the artificial intelligence world figured out is that, yet the neuroscientists are saying that the neuron in the brain is simply summing up all the inputs. Our models shows that if we assign them weights, so that it's not just the sum of x1 plus x2, but x1 multiplied by some weight plus x2 multiplied by some weight, that's what is behaving the neuron much more closer to what we observe. So far what I'm saying here is that a neuron, n possible inputs, each input gets assigned some weights. When you sum all those inputs multiplied by weight, that's your function, which is basically the neuron is doing it. Then you use a transfer function, and I'll explain that a little bit more, why we need this transfer function. One more thing that the research has shown is that there is a bias term that can be included. Now, theoretically, you can say that everybody has biases, right? We like something, we don't like something. So research showed that if you just take the inputs and weights, it may not give us the desired output. So our current understanding of a single neuron is that we need to introduce a bias factor, and that bias is introduced here. So what we are saying is that a neuron may have n inputs, but we add n plus 1, or the 0th input, which is a bias input already assigned to a neuron. So far so good? Yeah.
Sir, why we give weight for each ages? What is the scientific reason behind that?
Okay. All right. So I think I just try to explain to that. So when we are, let's go back here. I said function can be used to approximate a natural phenomena. Then we said, how do you know which function, right? We don't know which function. What we do is that we observe and then we try to fit a function. So why we chose to do it this way? Because this is the best way we know it's approximating how the neuron in our brain is functioning. You understand what I'm saying? Okay. So let's say, let me give a slightly different example here. We talked about the age and height. If you drop, or let's say, if you throw a projectile, you can drop a ball also. Let's say you drop a ball from somewhere, or if you throw a projectile, how does it trajectory look like? If you do the projectile, right? How do you know that? Because someone told you, right? How does that someone know it? Because they observed. They observed, and then they basically figured out that this is the trajectory of a projectile would be. It would depend on what angle you're throwing it, what's the velocity, and then they've calculated it, right? Take yourself 500 years ago. What is the scientific reason? There's no scientific reason. There's no science. That is the science. They observed by throwing it at different angle and different speed, this is where it's ending up. Then they come up with saying, can I fit a curve into it? That's how you got the equations. None of these things have come in pre-written from somewhere. When Newton discovered the laws of motions, it's not as if he got it in a dream. He started with an observation, then tried to fit a function, and then come up with a rule saying that what's the best way to approximate the behavior. That's what is happening here, right? So the benefit that you guys have, basically, you're seeing science being discovered now in a way, right? So there's another example, another benefit of these weights. I'm not, because if you ask question, let me just make the statement here. It will come in the next few slides. Where is the learning in this whole thing? So And I've asked this question a little earlier than I thought I will, but it's fine because you asked that what's the scientific reason for this assigning the weights. If we are saying that the neurons are the basic unit of how the brain functions or where the artificial intelligence is going to reside, where is learning happening? Sorry? In the optimization? Observations. See, observations are already known, right? So one way you can say that we can record the values we talked about yesterday, put it in a fact database, and that's also one way of learning, but it's more of a recall. We want to not only answer what's the value here, because that's an easy thing to say, that you minimize the mean square error and make it 0 because you have remembered or memorized every observation, and then given a number you give the right answer all the time. But that's not learning. That's not basically, you're not applying it to an unknown situation. Okay. I think a slightly better question or a derivative of your question would be that where do these weights come from? See, this is input. We know that. This is something that we have introduced in the sense that as we are trying to build this model. So if you think about it, the question that is, where do these weights come from? And that is a more interesting question to answer. Can someone guess where are these weights coming from? What do you mean?
They made a parameter to standardize the input.
To?
Standardize that input on online.
What is standardized? I haven't used that word yet.
Setting the inputs in a specific range so that the model can easily understand.
See, yes, I mean, in a way, you're giving the right answer, but you're using the words that we haven't introduced in the class yet, right? I mean, what does standardize mean, right? So, the weights is the learning, actually. So, we don't know the weights, right? Because we have introduced these weights. But, if we know that given certain input, what is the output we are expecting, what is the thing that we can modify to get this output? We can't change the input, that's given. We know what the output is needed. The only way we can change is either these biases or these weights. So really speaking, and I've jumped here a little bit, but that's where we will end up in another half hour. The learning basically is to learn the right weights and the bias values so that your output is same what you want. That's exactly what we will end up doing. Okay? All right. So I'll come back to it. Keep that in mind. So we have got these inputs. We have decided that we will add a bias term to it, and each of these things will be weights. The inputs are not directly summed up. They are multiplied with their associated weights, and then we get a function. Now, let's talk about this here. There's a transfer function. We can get a value of f of s based on the inputs and the weights, but it need not be constrained in the sense that, think of it this way. If you have a function of this kind, sum over 1 to n, x multiplied by w or xi multiplied by wi, that number can grow infinitely, right? Now, we do not want that. If we want to minimize this, so our domain, what we are saying here, this one, can have infinitely high numbers, but if you want to reduce it to a smaller size, because this would become input again to another neuron theoretically. So we do not want a system or a model where these numbers or inputs are monotonically increasing all the time. So we use a transfer function so that it brings back the output value into a desired range. Okay? We'll come to that in a bit. So all we are doing is that everything that I explained is listed here, and you'll get the slide as well, but just kind of go through it so that you understand. Weighted sum of the input, add its bias, passes the value through an activation function. That activation function will normalize or standardize, though both are not the official words used in the machine learning course. But then it will be going through an activation function so that your output is compressed into the desired range. Okay? The neuron fires means if the output is above 0, that means the neuron got activated. If it is less than 0, then the neurons remains in a sleeping state, basically. The bias is incorporated as a weight clamped to a fixed input of +1. So if the neuron is not, if you think of it this way, if the neuron was not activated and its output is input to another neuron, we need to give some value to it. That value comes from bias. So the bias is simply saying that if the neuron does not get activated, there is a certain amount of bias that we will provide. What is that bias? That is learning. It's simply saying that, yes, the neuron did not fire, but we know to make this model useful for us, we do need to add this bias. Inputs are flexible, real values. They may be correlated or independent, and they are all connected, the things that we just talked about. Let me just quickly go over, I think, some of these things that we have already talked about it. Weights, each neuron has an internal state. I just talked about what the internal state, functions of the input. The learning is happening from the data samples. They could be labeled or unlabeled, but for the sense of the class today, it's all labeled. Now, labeled samples is actually supervised learning. You know that, right? Because you know what, given the input, what's going to be the output. Adaptivity, in the sense that that's what the weights are coming in, because you're changing the connection strength to learn things. Learning is always to find out what the weights, what the value of the weights are. Non-linearity. Okay, now let's talk about the non-linearity a little bit. We talked about the linear function and non-linear functions. What is better, linearity or non-linearity? And think of it this way, all of it is purely artificial. What we are doing is that we are trying to scientifically or mathematically model a naturally occurring phenomena. It's in our hand how complex we want to model it, right? If we make it linear, it will be a lot easier. I mean, if you know anything about it, linear equations are easier to solve, quadratic equations are difficult, multinomials are even more difficult, right? Now we are saying here is that nonlinear activation functions are essential. Why would someone say, I want to make my model more complex than it needs to be? Or if it needs to be, why? Why is the nonlinear activation functions are better? Sorry?
Non-linear activation functions are better.
Yeah, but why? That's the question. That's a statement listed here. They are essential. Yeah.
Once it captures data.
Sorry? Think through it, whatever we talked about in the last hour or so. Learning, how does the learning happen? How it relates with rate of change? And what are the drawbacks if you're using linear function to approximate your phenomena? Okay, so on a high level what you're saying is correct, but again I'm going to use the terms because you're making it so definitive that it has already been proven. And I'm going to say that because we want to use these functions for learning, the learning is to discovering the rate of change. The rate of change of a linear function is a constant, right? This was a linear function. The rate of change is constant. If you use the linear function to approximate, there is only one speed or one way you can learn. We don't know if that is the right thing or not. So we do not want ourselves to be limited by or constrained by that a single way and single speed of learning. If we are using a nonlinear function, the rate of change can differ. Okay? Now that brings me back to the calculus part, that what is rate of change. Let's see if we need to do it at this point or we will come back a little bit later. All right, we'll come back to that, but think of it this way. Yes, you can use linear functions to approximate, but linear functions constrain you that the rate of change of a linear function is a constant, and you don't want that. You want your model to be more expressive, powerful, and able to represent the differential rate of change. Okay. Some of these functions, and this is relative here, the activation functions could be linear, threshold, sigmoid, etc. Has anyone heard of these functions called sigmoid, 10H, or what do these functions do?
Increasing functions, manage increasing functions.
They all are actually, but there has to be something else. All right, fine, we'll come to it. There are different topologies that we are going to consider, and as I mentioned that most of the research is in the sense that how do you structure these neural networks. There is a single layer feed-forward neural network, which is the most common. This is where we will progress when we go from one neuron to two neurons and so on and so forth. Multi-layer feed-forward means you have multiple layers, input layer and output layer, and in between there are more layers, which means that you have more functions which your input is going through. Recurrent network, which is basically providing a feedback path, something that we talked about yesterday. So the difference between this is that there is a feedback at the neuron level itself, and this is at the network level, there's a feedback. Okay? All right, so let's look at a few of the other things in terms of the artificial neural network. This is a generic schematic of a single neuron, right? I mean, majority of the information that's present here is something that we saw in the earlier picture. I'll just going to walk through how exactly this looks like. So what we had here, make sure that you understand this, because we're going to be summarizing, because this was one neuron, then we're going to basically use multiple neurons, so we won't be able to display all of it all the time. So make sure that you understand this one. What time do we break? Is this 11? 11:15? Okay. All right. Okay, so make sure that you have this in mind, and let's just try to understand how exactly this represents it here. So there are two things basically. Now this is a neuron which is in between the two other neurons. So it's somewhere in the middle. Y is always the output. Z is a neuron. There are weights which are assigned to the inputs. These are inputs coming in. They could be coming in from another layer, or they could be the most primary input in there. This is the bias function. So any neuron, you have three things: input, biases, and weights. Those are the three things that you will be calculating, right? And if you go back to the question that we started earlier, we are doing an intelligent system. We are trying to figure out what's the best network architecture going to be to arrange these neurons. And for each of these neurons, what's the weights, biases, and if there is any connection that is coming from the previous layer. That's what we are going to discover this, right? Supervised learning is where we will start. The learning is a process by which the network learns the biases and weights. That's all it's doing to begin with at the simplest form. So supervised learning is it's trying to figure out that whether whatever is the output is matching with the given or expected output. Back propagation is a problem that basically, or a method that basically lets you match with the desired output. The parameters of this network are the weights and biases that are learned between the input and the expected output that's required. The unsupervised learning basically says that we don't know the right label, but we will try to get as close as we can to the desired output. We don't know the exact desired output. Okay? Let's continue to do this. We try to optimize, and optimization here is minimizing the loss function, which is basically being done that by changing the weights. If you change the weights, you will change the output. You change the weights so that the difference between the actual and expected output is minimized. I've said this so many times, you should get this in your brain totally etched, right? Where it is, this model of neural network works best, where there's a high dimensional data, noisy data, imprecise data, or imperfect data, which is really the entire world basically, right? If we have totally precise data about the world or the phenomena that we have, we will not have any problems, right? There's one more thing here. This also works when we do not have a well-defined mathematical solutions or problems. Now, let me ask this question here. Has anyone heard the term closed form solutions or analytical solutions? So think about it. If you have a problem which is calculating the projectile, path of a projectile, there's a closed form solution available to it in the sense that there's a formula. You specify the initial velocity and the angle, you can calculate the entire trajectory and where it's going to fall down, right? The man has gone to the moon because for every problem that's there in between has a closed form solution. If you have a closed form solution, you can figure out the right angle and everything that's out there. When the rocket goes out, it is following exactly the same model, right? We know how the gravity functions. There's a closed form formula for gravity also. So everything is known there. We're not solving those problems. They have already been solved 200, 300 years ago. This is a solution where the closed form formula is not available. We don't know the answer to that question. So this is approximating. This is trying to find how exactly we're going to work with. Okay, I moved a little bit somewhere. Sorry. I think this one has come back. Yeah, okay. I think this one is also very sensitive with this move. Okay, all right. All right. So the last statement here, which is what we are trying to do, basically, how can we take these models and make the intelligent systems out of these? Okay, so next 4 or 5 slides will try to reset our problem as what we are doing. So most of you should find these somewhat repetitive because I have asked this question, AI systems, what are the steps involved? So it's a recap of that. Little bit modified to now talk in terms of artificial neural network, but it's still the same thing if you think about it. So let's try to go a little bit quicker. So the first problem that we solve is representation. How do you represent the knowledge? You need some kind of representation. Doesn't matter what type of data you're dealing with, chessboard, maze, text, object room. So doesn't matter what the field is, that you need to find how to represent the data. That's the most important part. Why? Because most functions of the AI is to represent the problem space so that you can efficiently search for best solution. Something that I've been saying, maybe this is the last day I say it because I hope that you will get it. That's what you're doing. Your representation should allow an efficient search. And then sometimes you need an output from that search. Sometimes the representation itself is an output. Does it have the answer? Okay, not a specific one. When the representation itself is the output. Can someone imagine? Let's say the intelligent system that you are developing is the software for a robot. Right? The representation of the robot's environment is output itself, because the robot has 3 things. It has sensors, it has mechanical movements, which we are not studying, that's known. All it needs to know then, if we can represent its environment in a way so that it can navigate itself around or search the most optimal path. So the representation is not just required for calculating the output, sometimes the representation itself is the output. Right? Okay, so that's one part of it. Let's just continue to look at what all is required for the intelligent operations here. Once you have that representation, goals and objectives, right? Sometimes the representation itself is the goal. If that is not the goal, then you're trying to figure out what the goal is. Best move, shortest path, parsing, recognition, localization, whatever the case may be. Now keep in mind, there are all kinds of problems you can solve, right? In a course like this, we can't really solve all the problems, right? Image processing is a problem in itself. Natural language parsing is a problem in itself. So there are a lot of different areas. I think yesterday we had a couple of slides in each of these areas, what all the intelligent systems can do. Or maybe this was, yeah, I think we covered yesterday. So starting from coding to the translation to the content generation, all kinds of things, right? So depending on what exactly your goal is, your strategy for the next move or best move could be different, right? If you continue on that, where exactly you're trying to figure out or how exactly you're going to determine what you're getting is correct. In the sense that not everything, this is an imprecise world, we don't have the data is noisy, the data has gaps. We do not have closed form solutions. We may have to actually figure out that is there a logic involved? Are there inferences that we are drawing based on the given data? Probability comes in. We may not have the definitive answer. Okay? We touched briefly on probability yesterday, I think, and day before. We're going to come back to it again. Why do we need probability? Because neither our data is perfect nor our understanding of the output is perfect. So in many cases, we will end up having a situation saying that we think there's a 90% chance that this is the correct answer, or this is the 30% chance this is the correct answer. So we will need some kind of probabilistic inferences to figure out what our output is doing here. Learning how exactly we can continue to adapt the internal representation to change the learning, continuous learning. I don't know whether this screen has this or not, but it doesn't matter. But as I mentioned earlier, even if you have trained your model, when we took the example yesterday of these base or foundation model, they have been trained, but to get the right answer that you're looking for, when we were talking about prompt engineering, you may need to continuously train the model as to make sure that it does the right thing that you want it to do. So we need to continue to make sure that if the world is changing, if the job you're trying to do is changing, should be a way so that the model is continuously evolving and or learning, right? The next thing basically is that the output itself can be, it could be as simple as yes or no answer, 0 or 1 output, or it could be as complex as anything. It could be finding out the next word, next sentences, building an audio stream or a video or an image. It could be anything. So even though we have tried to simplify it by breaking down to a neuron, and then the output is simply summing up the inputs multiplied by weights and biases, we got to find out, can that model be generalized to solve all of these problems? Because our output is not just that. Output is not simply saying that I give you 2, 3, 4 as a number and you give me the answer as 2 plus 3 plus 4 as 9, right? Can we do that or not? Any questions at this time? Think of it this way. I have told you everything that is needed to do all that you're seeing in the world today, in the world of machine learning and artificial intelligence. They're all going on this method only, just doing this simple arithmetic. So any questions? If not, then I'll ask you guys a question a little in a minute or so. Yeah.
Previous slide. Sir, Jackie told me why you take a weight of, but I want to know why you take a bias of issues.
We'll come to that. We'll show that. So understand two things at this point of time, and I think I answered your question as well. When you said that, is there a scientific reason, right? See, the only scientific reason is that that's what you're discovering. What we are learning here, so think of it this way. What we are trying to do is, can we train a neural network to become an Einstein? Actually, there are research papers to say that, can we train neural networks which can determine these laws of motion? And this is not new. The fundamental laws of motion, the 3 laws of Newton's, were discovered by neural network, I think 5 years ago. So if you think about what I'm saying here, We have already trained a machine to act like Einstein. Given sufficient learning, it will discover the same laws of motion. Make sense? Right? And what are those learning? The weights and biases. So the question is that why do we add bias term? Because that's what we have observed that it's working correctly. It's working for us. One intuition that I can give you is that because these neurons are connected in a sequence, if the other inputs are all 0, you do not want the 0 to be output, you want some bias to be added to it. That's what it is. Okay. Any other question? Yeah. Yes.
If we go 5, 6 slides back, there was a second picture of neuron. In that picture, there are some red arrows that are directing outwards.
Oh, this one? Yeah.
What they were.
Okay. All right. So I did not touch upon this because we're going to come back. So all of these networks work in two different ways. We talked about back propagation yesterday, which is really combining the feedback, and the feedback is basically going to adjust the weights because that's what your learning is. So the feed forward is that all the input is going in the forward direction, and then you have the loop or a back propagation, which is basically telling you how much you need to adjust weights so that your output is matching with what the input is. We'll come, yeah. Yeah. This is, okay, so this was a generic representation of one neuron in between multiple layers. This is one neuron, yes. Okay? All right, any other question? Okay, so now let me ask you the question. How many of you think that this is indeed a very, because this looks very simple, right? All we are doing is simple mathematics. Fine, there is some calculus involved, some functions are involved, some probability is involved. Is it really all the thing that's needed for learning or machine learning? Do you have an example where such a simple thing actually can do very complex things? Yes, no, maybe? I'm just asking one. I could have asked 3 examples. Okay, let me give you one, and then you come up. Yeah, sorry.
We can use medical thing, like we predict the cancer before it.
Okay, yeah. So let me say one more thing here. Actually, has anyone heard the term called Occam's razor? Okay, that's one of my favorite. In my class, I always use this. You should Google this. So what the Occam's principle says, or Occam's razor says, that find a solution, but don't make it simpler all the time. Or put it different ways, that if you have 2 options as answer, pick the simpler one. It will always work. Okay? Why am I saying this? Yes, you're giving an answer, but then you could have chosen a much simpler answer. I'm a representation of what? Cells and connections, right? Everything is in our body is basic simple cell. So if you start from a very simple mechanism like a human cell, then you have the entire body, which is a fairly complex mechanism, right? So that's one, but you're not all medical students. How is a computer function? What's the fundamental building block of a computer? That's not the building block. Sorry? Gates. What is a gate? Right. So how many of you think that, or when you first time learned about the gates, that these simple gates, because those are the only thing that's out there, and then you have the supercomputers. What are the different gates? And, or, and? Okay, NOR is the negative of this, so NOR and AND. One more fundamental gate. Yes. Right? So if you start from there, if you learn the digital, whatever the course name is called nowadays, but digital computers, right? That's where you start, right, with these gates. And starting from there, you can build a microprocessor, microcomputer, supercomputer, whatever you want. At the end of the day, these are just these gates. You can think of these neuron is like these gates. All you need to do is to find how to put those neurons together just like these gates to build these massive computers. That's what you end up doing. Okay? And let me give you a little bit hint here. I'll come back to these gates. Okay? So I'll ask you what these gates do. All right. Any other question? Okay, if not, let's move on to the next module. So what we're going to do now is that we're going to take the neural network and drill down a little bit deeper and try to take that to the natural language models, right? Because the language models is where we want to be. This is a slightly better picture of the neuron. Again, this is what the neuroscientists have told us. And we are trying to mimic or model this. Now, we're not going in all these details. For us, this translates into this. This is again the same representation of a single neuron. Spend like, let's say, 30 seconds to make sure that you understand. If you don't, ask me the question, because as we are going to build the network, each individual neuron will keep shifting or keep kind of getting condensed. So make sure that you understand this. So one simple thing that has happened here, instead of displaying it horizontally, now it's being displayed vertically. So that's one obvious change that's there in the representation. So you've got the inputs. There are weights associated. This is a bias. Bias always assumes an input of +1, so that the bias value when you multiply gets added here. You have a summation function, then you have a function which is called sigma here, which is changing the output of this summation into the desired range of the output. That's what we have defined the neuron for. All good? Okay. The input layer is what is at the very bottom, which is what we call the inputs. It's a vector. Now, everybody knows what a vector is, right? As against a scalar. A single number is a scalar. If you have a set of numbers, you call it as a vector, right? The next one is weights. The weights are summed, so there's a weighted sum. One thing that is not listed here is that determination of the weights is what is learning. That's what is the learning, right? Then we do a nonlinear transform of that weighted sum. Why do we do nonlinear? Because we want our learning to be not restricted or constrained by a constant. Because if you take a linear function, its derivative is a constant. So we want a nonlinear transformation. And then finally you get the output. That's what each neuron is doing. You have inputs, you have weights. Weights is what the learning is. You sum them up, then you use a nonlinear transform. We want nonlinear transform so that the learning is differentiable, not constant, and then you get an output value. That's all we are doing in each neural network. So if I go back to the same question, what is the changing here, or what you can change? You can change weights. You can change the nonlinear transform function. Input is what the input is. The sum will always be done, and you have an output value. So far with me? And there is a bias. We talked about bias, like why. Now why, the only answer to the why is that because that's what the model works best. That's what we have observed, that we need to add a bias term. Okay? Now, let's turn this into a mathematical or the equation forms. The weighted sum of input and a bias. So the W represents the weight, the X represents the input value, B is the bias. So the summation function is Z equal to B plus summation of Y multiplied by X over all I's, right? If you think that everything can be converted into metrics, which it can be, it's a column or a row matrix, it's a vector, which means it's a matrix, you can write it as Z equal to W multiplied by X, where both are column matrices, and add a scalar bias function. Make sense? Rather than using that summation function Z, we are going to use a nonlinear function F so that we can compress the output into desired range. Is that clear? So, in a way, you can describe the entire mathematics of a neuron in this statement or this equation. Is that part clear? All right. Now, what things can change? We talked about that you can change the weights and biases, but the weights and biases are changed based on the learning. What's in our hand, what we can change is the choice of the nonlinear transform. We did talk about that we don't want linear, we want nonlinear. What possibilities exist to choose what nonlinear transformation function we should use? Any idea? I mean, partly I mentioned that it depends on what our goal is, and clearly we don't want the linear functions, right? So one of the functions that you may have heard is called sigmoid, right? The sigmoid basically looks like this when you draw it over a range of values. Its equation is this: 1 over 1 divided 1 plus e to the power minus z, where z is the value, right? Now, if you ask me what's the scientific reason of using sigmoid, we don't know. I mean, there's no reason. It's just like that it's discovered that this is a good function. We can get the intuition of why this is a good function. Sometime it is, sometime it is not, but let's see. I mean, it's not always used depending on the type of neural network. Other networks have been used, but for the first use case of LXNet, which was, or ResNet, which was used the first time the deep neural networks were found to be useful, sigmoid was used as the activation function. So if this is the function, and the really what the z stands for is w multiplied by x plus the b, which is the bias function, it's becoming, this is the actual calculation if we are using the sigmoid as an activation function. Now, what is sigmoid doing if you think about it? It's compressing whatever is the value you give to the z into 0 and 1. That's what it's doing. So if you are taking the output of your summation of a neuron, pass it through a sigmoid, you guaranteed that your output would be between 0 and 1. Why is it important or relevant?
Because it gives only probabilistic values.
Sorry?
Probabilistic values.
Yes and no, both. First reason, the basic reason, what we said that neuron in our brain are in two states: activated or not activated. So if we have the output as zeros and ones, we are approximating the B neuron better, rather than having a value of 4, 6 or -4, -6. You don't know what's activated, what not activated. So really speaking, the sigmoid as a function is taking any value and compressing it between zeros and ones. So that tells us that we can approximate its output as if it's indicating whether a neuron is activated or not activated. So far so good? Let's take an example here. Let's say you have a unit, a single neuron. The weights assigned to that are 0.2, 0.3, 0.9. That means there are 3 inputs. There's a bias of 0.5. This is somehow learned. If you give it an input 0.5, 0.6 and 0.1, the output will be here 0.7. I mean, you can just trace it down because This is the y function, this is the sigmoid function. You put the values of w, x, and b as represented there. This is what you get, and you calculate, and you get the number 0.7. Right? And this is a simple calculation that is happening all along in the neural network. That's all is going on. So far so good. So you now understand how the simple mathematics is functioning here for each neuron given inputs, weights, bias, output, and a sigmoid function. Is sigmoid the only function that you can use? Right. So theoretically speaking, as I said about an hour ago, that given a set of problems, there are infinite number of functions that you can find. You need to find which one works best for you. Now, some of the machine learning research is in discovering what's the best function, because we don't know yet. We have not reached to the point where it's the Einstein's theory or the Newton's laws of motion. We have not reached that point yet. We are still discovering, right? So sigmoid is one potential option or one function. There are other options here. 10H is another function. Now, if you think about it, each of these functions, all they are doing is that they're mapping a domain to a range. Our requirement is that the output should be between 0 and 1 or -1 to 1, something so that we can differentiate between when the sigmoid, when the neuron is activated or not activated, right? There's another one called rectified linear unit, ReLU. This is also a function that's being used in some neural networks. What this one does is that it has 0 for some values, and then it just moves to 1. Now, if you notice that each of these functions have different kind of behavior at different points, right? This one here. Now, one of the things usually that you will learn in mathematics, and even otherwise actually if you're doing the applications of the math, is to understand which function approximate the phenomena that you're studying better, because that's what these functions do, right? So you would see that, and I'm not going into the detail of the math there or the functions, that in some cases you will see that 10H works better, some cases the rectified linear unit function works better. Later we will see some cases and some intuition why one of them is better than other. Okay. All right. Let's come back to the gates. Yeah. Why? Because we know that if we can build the unit of the basic gates, then we can perform any computation, because that's how we have seen in the last, let's say, 70 years, the computers have worked with starting with the basic units, right? Can we say that our neural unit also perform the same functions? Because if it can't, then obviously we don't necessarily have the right fundamental building block. So everybody knows these AND gate, OR gate, and exclusive OR gate, right? Yeah? That's the truth table, or the values given the input x1, x2, what the output would be for the AND gate, OR gate, and exclusive OR gate. All right. So the question I've posed already up there. If we think that our neuron can solve all the problems of the world or learn everything, the very first question to ask is that, can it learn how these gates function? Because if it cannot learn even that, then we have a problem. So think of it what I'm saying. When these gates were designed, they were mathematically designed, right? AND OR, exclusive OR. Physicists or electronic engineers found a way to implement them in hardware. And that became the fundamental building block of a computer. Now we are saying that, and the computers were then used to train, like you wrote, the algorithms to have them do all kinds of things. Now we are saying is that we're trying to build something where we don't need to program it, can it learn on its own. very simple, obvious question is that whatever first building block that we are coming up with the neuron, can it actually do the AND OR gates? Because if it can do this, at least we have a theoretical possibility that it can do bigger things. If it can't even do this, then you know that you haven't really figured it out right. So, what do you guys think? Can it solve these problems? The neuron that we saw up until now. First of all, how will you implement an AND gate with a neuron? Let's do this. The difference here is that we don't want to build. We want the neuron to learn how to mimic an AND gate. That's the learning, right? And what was the learning I said? Biases and weights. Can a neuron find the right values for biases and weights so that it can approximate, not approximate, it can replace an AND gate? Yes, no, maybe? Okay, OR gate, exclusive OR gate. See, another thing that I'll say that when you are coming up with some new idea in a research, you're trying to find the simplest possible equivalence which you can show that if I can show you my device can do this, that means everything that you can do with that, you can do with my device also, right? So if I can show that neuron can actually implement all of this, anything that you can do in electronics using AND OR, exclusive OR, I will theorize that my neuron can learn to do it. In the case of this, in electronics or in computer science, somebody wrote it, somebody actually designed it. I'm saying the neuron can actually learn it, right? So this was the neuron basically, 0 and 1. This is what we are trying to figure out, no nonlinear activation. It's very simple. We're simply saying that the output is 0 if the output is less than equal to 0 or it is greater than 0. And what we're going to do, we're trying to learn the weights. And this is what it turns out to be. AND gate, you need the weights of 1 and 1 and a bias of -1. For the OR gate, you need the weights of 1 and 1 and the bias of 0. So you can, your neuron can very quickly learn how to approximate AND and OR gate. How about exclusive OR? Okay, before we go on the exclusive OR, can anyone see the problem? What the problem might be with exclusive OR? There's also another issue there in the sense that there's another term here called perceptron actually. I have not introduced the term perceptron. The perceptron is the first implementation of neuron. It's for historical reason it's called perceptron. Neural networks are also known as multi-level perceptrons also because that's just simply saying that the perceptrons are organized. Okay, if I go back here, think about it. The constraint is in no nonlinear activation function. We wanted to simplify. Why? What is a linear activation function looks like, or a linear function looks like? A linear function is a line somehow, right? That's what it is. Can you implement exclusive OR so that the line can distinguish between the output 0 and output 1? That's what it is. The line here acts as a discriminator function or a discriminator. I think somewhere we'll see. Yeah. So the perceptrons are linear classifier, or the neurons are linear classifiers. Even though we are using the non-linear function, activation function to learn something, but in general, a linear classifier is simply kind of saying that given a line, it will tell you whether a point is on this side or on the other side. That's what zeros and ones are doing. The same equation that we have seen can be rewritten in a standard linear format, y equal to mx plus c. M is a slope, c is the intercept, right? B, the bias term, is the intercept here. The differentiation is really the slope, that's m. So the line acts as a decision boundary. Why the exclusive OR is a problem? So if you do the end function x1 and x2, you end up here, because if the input is 0s and 1, right? If both are 0, you'll end up here 0. If any of them is 1, the end will be, this will be the output. You can find a function. There are infinite number of functions that can implement this. If it's OR, this is how the line will look like. Anything, this side will actually be able to classify. Exclusive OR is a problem. Exclusive OR is saying that the output is 1 when any of them are 1. There's no linear classifier that can actually implement this function. So what are we saying here? Our neuron, if it is using a linear classifier, it cannot implement the exclusive OR functions, because the exclusive OR function is not something what is called as the linearly separable function. So now we run into our first problem, that if we were trying to use the neurons to implement the basic gate functions, these are not sufficient. What can we do? What do you guys think can be done to solve this problem? All right, we don't need to do the same research ourselves, but some people thought about it, and then they said, wait a minute, if we introduce a layer in the middle, we can actually implement the exclusive OR also with the same building blocks. So what's going on here is that's where now the rectified linear unit comes as the activation functions. It's a linear function. Now if you introduce a hidden layer, that hidden layer can actually let you implement the exclusive OR functions. What you notice here is that these are weights. The x1 and x2 have weights of 1 and 1, and there is a hidden unit which has the biases of 0 and -1, and then there's an output unit which has a bias of +1. If you do the calculation, this implements the exclusive OR function. So I'm not doing it here. Take it as like an assignment, that work through the numbers and see that these sets of weights and biases actually let you compute the exclusive OR functionality with one hidden layer, right? Now this is called a two-layer network. The input layer is not counted. It has one output layer and one hidden layer. So if you notice that, and then that basically tells us that, great, we can actually do both. Okay? So this is exactly what is happening. The original space was like this, and you created a hidden space that basically now separating the two different layers here. Can someone tell me what exactly you think is going on here? Because that's very key learning actually for the researchers it was. So we were limited here by the dimensionality of the data. If we look at it in 2 dimensions, this is not separable. What these researchers discovered, that by introducing a hidden layer, what we are doing is that we are increasing the dimensionality of our observation. So 2 of these functions which were not separable in a 2-dimensional space, when you introduce a hidden dimension, they became separable by a linear function itself. So the learning here was that if you increase the dimensionality of your observations, you could potentially use simpler discrimination functions to isolate them or divide them into different groups. This is a very key finding, and then this would help us learn about language models as we go along. Okay? So let's see here. This was the last line before we take a stop. So what is happening is that this was the original space. We couldn't differentiate. When we introduced the etch space or the hidden layer, or what I used the term yesterday, the latent space, something which was not separable in two-dimensional becomes separable in higher dimensions. That's what we are doing. So what we are going to do is to figure out that how to effectively utilize hidden layers to learn more about whatever we are trying to learn. Okay? So any questions so far? Yes, no, maybe? Don't be afraid. As I said, that today is the most math heavy day, but once you get through today, hopefully it should become easier as we go along. Okay? We will get in algorithms and some data structures as we move along, but let's stick today for some math. We're going to talk about calculus and differentiation a little bit more when we come back. I think it's a good time to stop. Think about it. If you have a question, don't necessarily force it, but when we come back, I'll start with if you have any questions. So think through what we have learned so far. Okay? Yeah. All right.
We'll reassemble at 11:30.